The retaining wall demonstrated would not make the best dam because of two main reasons. Firstly, a dam's curvature is what allows it to resist bending and the force of water it holds, but the retaining wall demonstrated lacks this curvature and is flat. Dams need to have curvature and be stronger because water exerts a greater horizontal force than soils do in retaining walls. Therefore, a much more secure wall is needed to hold back water than to retain soils. Water exerts a larger amount of horizontal force, and the wall demonstrated only relied on friction to prevent its motion, making the wall an unsuitable dam. One strategy for retaining wall design is to make the wall have a tilt. This way, the horizontal force that the soil exerts is resisted by the shape of the wall, and the wall will not deform as easily. The model could be modified by bending the vertical wall or shaping it so that it has a tilt.
We placed the dam in using the leg-in design. This is because the weight of the marbles on the bottom of the leg would create a moment on it, holding it in place better. And from this, we can conclude that the retaining wall functions better with the base facing in, again due to the moment pushed on it from the soil or marbles, the weight of it pushing in helped the dam stay up better.
It is harder for the wooden wall with the short leg to tip over, because on top of the soil resting above the longer leg, which provides a counter-momentum to the sideway pressure. The short leg on one side also provides a reaction force to further stabilize the structure. However, when we move the wall closer to the side of the tank, the walls fails because of the increased height or depth of the marble. After we removed the mat, all the walls failed. They were either pushed back or tipped over immediately. The reason behind this is the loss of friction on the bottom of the retaining walls. Friction is crucial in maintaining the equilibrium of the system because it is the only force on the x-axis counteracting the sideway forces generated by the soil. Therefore, if it is removed or greatly reduced, the system will begin to move. There are many ways in which a retaining wall can fail. Since the retaining wall is designed to counteract against the sideway pressure generated by the soil, it fails when it can't provide enough force or moment to maintain the system equilibrium. The result can either be that the wall starts to move because it failed to provide enough reaction force in the x-axis, or the wall tips over because it fails to provide enough counter moment. Another way the wall can fail is when it cannot carry the bending force anymore, in which the wall breaks in half.